Hi, hello, Shamala.
Hi, hi.
Uh, Hi, Azri.
Can I try sharing my screen for a while?
Yeah, why not? While we are
Okay.
waiting for everyone else.
Yeah. Yeah. Okay. So it's viewable, right?
Sorry, Shamala,
Is
you
it?
were saying?
It's viewable, right? You can view it.
I Yes, I can view it.
Okay. Okay. Okay then. Thank you. I stop sharing.
No problem. Totally. Hi, everyone.
Hi, Roman.
Hi, good evening.
We are still waiting for our chairperson,
Huh?
and we are still, yeah. Dr. Study is our chairperson.
Oh, I
I
see.
think my colleague Nurul Azri is currently reminding him. We are also short of one more evaluator,
I see.
so we will begin as soon as they arrive. Thank
All
you.
right. All right.
Just wait a bit. Hopefully everything goes well.
Prof. Study is here. Prof, can you ask?
Prof, if you still have a problem, you can try a few options. One is refreshing your browser, and two is actually to exit one session first and then just come back. Thank you, Prof.
So, Longman,
Yes, Doctor.
this section only one evaluator.
Oh, okay. Dr. Asad is not here?
I'm not so sure.
Okay.
I
Doctor,
contact.
Doctor, was that a question or was that a statement?
Question.
Okay, my bad. Okay. Okay, Prof. Study is coming. Okay. There's supposed to be one more, Dr. Asad. Yes.
Oh, I
Go on,
see.
sir.
All right. All right.
Hello, Prof.
Hello, good afternoon.
Good afternoon, Prof. Prof,
Sorry,
you may,
I have
no,
problem to connect.
no problem, Prof. It's okay online. Prof, you may say anything you want as a chairperson
Yes.
to start the event. We are still waiting for one more evaluator, Dr. Asad. So I think we have to wait for him for a bit since
Yeah.
he's an evaluator. So we'll give him 1 or 2 more minutes while my colleague look for him. Hello, Doctor. Okay, Prof. Our evaluators are all here. Our chairperson, you,
Yeah.
is also here. So I think we can begin whenever you're ready, Prof. Thank you so much.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. Very good afternoon, ladies and gentlemen. Welcome to the first Malaysia International Conference on Nanotechnology and Catalysis. We are now in the parallel session 3, entitled on the chemical kinetics and catalytic activity. My name is Istadi, and I am a chairperson at this parallel session, and I'll be the session chair today, together with the session moderator or IT personnel, Ms. Nurul Azri and Mr. Muhammad Lokman. Thank you. I will invite the speaker and presenter to request to share the audio and video now one by one. I will call the presenter one by one. We have 3 presenters here, Miss Samala, and then Miss Lama Alafandi, and Mr. Muhammad Lokman Hakim. And we have one invited speaker, Dr. Wei Fun Lee. So we begin to the first presenter. I will invite Miss Samala Gori Krishnan to deliver your presentation. You will have 15 minutes to present your works, and will be continued 5 minutes for ask and question.
Okay.
For Ms. Samala, time is yours.
Thank you, Prof. Ishadi, and a very good afternoon to everyone and my fellow researchers. I am Shamla Gauri from University Tenaga Nasional, Unit 10. I would like to share my research finding on esterification reaction catalyzed by oil palm EFB supported magnetic catalyst optimization using response surface methodology. This will be today's presentation outline, and I will address accordingly. To begin with, Malaysia is one of the largest oil palm producer, and as well as oil palm waste. And the minimal utilization of this waste, especially EFB fiber, which is mainly used in as a source of heat and power in oil palm mills. Heterogeneous catalyst, which is physically different from a homogeneous catalyst, forms as a solid, where the catalytic reaction occurs by the absorptions of the reactants on the solid surface, where it helps the reaction enhance the reaction. Moreover, magnetic catalyst as an added advantages in terms of rapid separation and has a minimal catalyst loss for the post reaction. The catalyst can be further used in a biofuel application, where with this, a solid catalyst can be used in esterification reaction, which produces alkyl ester and water as a byproduct. Here is a simple reaction, simple diagram that shows how the magnetic separation can be done. There are 2 problems. Firstly, it's the effect of catalyst in the esterification reaction, where the excess homogeneous catalyst is difficult to be recovered and consequently generates a lot of generates more wastewater and has no reusability. Secondly is the minimal utilization of oil palm waste, where the production of oil palm waste increases annually. Here, in 2020, 7.3 metric tons of EFB fiber have been produced. And the statistical data from the Department of Statistics Malaysia shows the production of fresh fruit bunches increasing annually. Based on the problem discussed, we aim to synthesize and characterize EFB fiber-supported magnetic acid catalyst and to optimize the reaction parameter using EFB fiber magnetic acid catalyst by response surface methodology. To execute our aim, here is a brief flow of methodology from the oil palm EFB fiber chemical pre-treatment using sodium carbonate, and the treated fiber will be used in magnetic acid catalyst preparation by one-step impregnation method, and its utilization in esterification reaction to study its effect in the catalytic reaction parameter by Box-Blanken optimization design, and finally to examine the catalyst recyclability. The results and discussion separated into three parts. Part A is the catalyst characterization. Part B is the esterification reaction on the Box-Blanken optimization design, and part C is the catalyst recyclability. For results and discussion, in part A is the catalyst characterization. The first characterization is morphology analysis. The SEM image of untreated EFB fiber reveals that the fiber has silica bodies and impurities on the surface. While after the sodium carbonate treatment, the silica bodies were removed and observed the appearance of empty pores on the fiber surface. The treated fiber was further used for the impregnation process, where the particles were embedded on the fiber and the surface of the fiber much grosser. Continuing to the Edx analysis, where the treated fiber has high composition of oxygen and carbon, while the presence of iron and sulfur in catalyst shows that the fiber has been successfully impregnated, and the presence of sulfur and oxygen indicates the acidity of the catalyst, while the presence of iron and oxygen content indicates the presence of magnetic properties. With this, the catalyst achieved a 2.4 millimole per gram, acidity of 2.4 millimole per gram, which indicates the presence of sulfonic group. And the determination of magnetic compound in the catalyst was confirmed by XRD analysis, where it shows that the catalyst as a megamite particles of iron oxide with cubic structure. And the catalyst also had a very high soil surface area of 188.87 meters square per gram with a pore volume of 0.1358 centimeter cube per gram, which indicates that the active site can be easily accessible to the reactant for a reaction to occur. And the rapid separation and the easy separation of the catalyst can be explained by the presence of strong magnetism in the catalyst with 24.97 EMU per gram. The functional group in the catalyst were determined by the FTIR analysis, and the existence of the two bands at 1110 and 1026 was attributed to the presence of sulfonic group, and the band at 542 indicates the presence of ferric oxide. Moving on to the part B of results and discussion, a set of 17 experiments were generated, and the experiment were conducted based on the arrangement. It was observed that a maximum esterification rate of 94.9% was obtained at the optimized reaction condition of 9 weight% catalyst loading, 12 to 1 methanol to oleic acid molar ratio for 2 hours of reaction at the fixed reaction temperature of 60 degrees Celsius. Based on the optimization results, analysis of variance, or ANOVA in short, were conducted, and it was observed that the model is significant as the p-value is less than 0.05. Besides, all the primary factors were also significant along with the interaction factors AB, AC, and A square, B square, and C square, except the methanol to oleic acid molar ratio with duration interaction, which the p-value is more than 0.05. Moreover, the statistical analysis of regression coefficient shows the R square value is more than 99.93%, which indicates the model, the output response is significant and the model is fit. Besides, the correlation variation, the CV percentage, was 0.14%, where it indicates the model, it has a good fit model and it's reliable. Here is the optimization of 3D surface, where in the interactions between catalyst loading and methanol to oleic acid molar ratio contributed to a high esterification rate of 94.9% with 9 weight% catalyst loading and 12 to 1 methanol to oleic acid molar ratio. While the interaction between the catalyst loading and the reaction duration will also achieved a high esterification reaction of 94.1% at 150 minutes and 9 weight% of catalyst loading. However, a weak interactions were observed between the methanol to oleic acid molar ratio and the reaction duration. But the esterification reaction were also high at 93.9% at 2.5 hours of reaction for 12 to 1 methanol to oleic acid molar ratio. With this, based on the optimization study, we can say that the catalyst loading has the most influential parameter in the esterification reaction, followed by methanol to oleic acid molar ratio and reaction duration. Lastly, part C is the catalyst recyclability. The magnetic catalyst was able to be reused up to 5 cycles with a reduction in the esterification rate to 83.9% at 4th cycle, and it remained in the similar value at the 5th cycle. It is worth mentioning that the catalyst was still able to separate magnetically. In conclusion, the EFB fiber supported magnetic acid catalyst was successfully prepared by one-step impregnation method and characterized by various analysis. And based on the optimization results, we found that the highest esterification rate of 94.9% achieved at the optimized parameter of 9 weight% catalyst loading, 12 to 1 methanol to oleic acid molar ratio at 60 degrees Celsius for 2 hours of reaction time. And biomass-derived magnetic catalyst can be separated easily and reused up to 5 cycles. I would like to end by thanking the finance provider, the Ministry of Education, my university, for the assistance and resources. Here is the list of key references. Thank you.
Thank you very much for Ms. Samala for addressing this interesting topic. Ladies and gentlemen, now we come to Q&A session. I will read the question from the chat banner or chat window. Any question from for this presentation?
Hi, good day. Thank you. Thank you for the presentations. I'm Lee. I have a questions
Yes, Doctor.
regarding to the EFP biomass.
Yeah.
Is it a kind of catalyst support?
Yes, I use it as a catalyst support.
Okay, so do you perform any thermal calcinations before impregnations with the iron salt?
Actually, I did calcination after the impregnation process, which means the final stage.
Okay, so what is the temperature that you use for these calcinations? Because yeah, the EFP is quite to decompose, right? In between 300 to 400 Celsius.
Correct.
Right.
No, I used 500 degrees Celsius, but previously we have studied on the effect of calcination, and and also I did a optimization study. With that, we found that the 500 is optimal for the catalyst preparation, and we also observed the particles were also the fiber. I mean the size by the SEM image. We found there is no thermal degradation.
I see. So it is. Can I just this is the last question. Can I say after the thermal treatments for this EFP biomass, it is kind more on like the carbonaceous materials, right? Carbonaceous.
I think carbonaceous material is when we want to like let's say we want to do a pyrolysis, but at this stage actually we want to have a good arrangement of particles on the fiber when we are coating on the fiber, and to have a good attachment. That is our aim of using a calcination at the last part of the catalyst preparation.
Okay, thank you.
Thank you, Doctor.
Okay, thank you. Any other question?
Hi, Miss Samala.
Yes, Doctor.
Yeah, I'm Maurice.
Yes,
So I
Doctor.
just wonder because I saw just now your performance of the acidification is quite good. But I want to know is how good when is compared to the commercial available technology.
Okay, for the commercial catalyst, I have studied on the commercial catalyst previously, and we found it is much more better. Because we found that we used ambulase before, so we found that this catalyst is performing much better than the ambulase before. Yeah.
I see. All right, thank you.
Thank you, Doctor.
Thank you. Any other question? I have a question, Ms. Samala.
Yes, Doctor. Yes, Prof.
You state that the model in RSM is significant to
correct.
present the experimental data. Can you justify using the ANOVA and R squared? What is the value of the F value of the ANOVA and R squared?
ANOVA and R square, because based on the ANOVA, the p value is less than 0.05. So the R square is it says that the accuracy of the model.
Yeah.
So which means if let's say it's 99%, which means the model is accurate enough to be used in this study to determine the interactions. So that is the based on my knowledge, I think that is the correlations. Yeah.
Okay. Any other question? Okay. If there is no more question, I think the presentation session for Ms. Samala is finished. And let's give applause to Ms. Samala. Yeah.
Thank you, Prof. Thank you.
Okay. Now we move to our next speaker. Next speaker is Ms. Lama Alafandi. She will present green synthesis of silver nanoparticle using the coffee extract for catalysis. So, to Ms. Lama, time is yours.
Good afternoon. You can hear me?
Yes, Miss, we can hear you.
And the slides are okay and moving?
Yes, it is moving. Don't worry.
Okay. Salam and good afternoon, everyone. Thank you for being here to listen to this presentation. This is Lama Al-Afandi. I am fresh graduate from IIUM, and this research is part of my final year project. So the research here is titled by Green Synthesis of Silver Nanoparticles using Coffee Extract for Catalysis. This research was prepared by me and with the generous help and supervision of Dr. Rika Rahman and with the help of Dr. Nurul Sakina and Sister Ainul and Dr. Muhammad Sufri, which helped with the TEM analysis. The presentation outline will be first introduction, objectives, methodology, results, and finally conclusion and recommendations. First of all, why did we choose silver or fabricate silver nanoparticles for this research? As we know, silver has many properties, and those properties allow it to be used in the industry for applications ranging from textile to biomedical application. Some of the properties are the antibacterial property, the anti-cancer property, the anti-coagulation property, and the catalytic activity. And in this research, we are interested in the catalytic activity of silver nanoparticles, especially they are synthesized using a green method, as we are going to test the silver nanoparticles as a catalyst to reduce methylene blue dye. The introduction is conventionally, silver nanoparticles and commonly are produced using chemical routes with the presence of harsh and strong reductants, such as sodium borohydride, and that requires sometimes heating treatment methods that often produce hazardous byproducts. In order to reduce the environmental impact, green routes have been encouraging based on the green chemistry principles, such as reducing the use of hazardous chemicals and organic solvents. Therefore, to eliminate those disadvantages of the chemical routes they are used to synthesize nanomaterials, there is a huge interest in the biological methods, which are considered a green routes of synthesis. Biological methods are such as bacteria, algae, fungi, and plant extract. During this research, we are interested in using plant extract for various reasons, and we are going to use coffee extract. Why do we choose plant extract and coffee extract? Obtaining the plant extract. Here we see some disadvantages of the previous mentioned methods, such as bacteria, because the production process requires more aseptic techniques and higher cost of product isolation. Therefore, many scientists prefer to use plant extract due to various advantages, such as a non-toxic and environmentally friendly, fast rate of growth, easy to scale up, and easy to obtain the extract. For example, here using coffee extract, we only needed to get the brewed coffee from the market. We need to filter it, to dilute it first with ultra pure water. Then we precipitate it for a few hours and then filter it, and it will be ready to use as a reducing agent. Some other advantages of plant extract: that plant extract consists of carbohydrates, flavonoids, and some alkaloids, such as caffeine in coffee extract, and they are capable to act as reducing agents or stabilizers during the synthesis of nanoparticles. Therefore, we can conclude that the aim of this research is to synthesize silver nanoparticles using a green synthesis method for catalysis. And the two main objectives of the research will be studying the relationship between the parameters, which are temperature, time, amount of extract, pH, and the formation of silver nanoparticles. Also, to evaluate the catalytic properties of the synthesized silver nanoparticles in the reduction of methylene blue dye. Moving to the general overview of the methodology, first, here we obtained the coffee extract. As mentioned before, it was diluted with ultra pure water, precipitated for 48 hours, and then filtered, and that's how we got our coffee extract. After the coffee extract is ready, we used Folien test to test the phenol content in the coffee extract and GCMS to analyze the content of the coffee extract. Then coffee extract was added to the silver nitrate to synthesize silver nanoparticles, and we will go more in details about the parameters of the reaction in the next slide. After we synthesized the silver nanoparticles, we went for characterization using UV-Vis and TEM. And then these silver nanoparticles were used as a catalyst to reduce methylene blue dye to a colorless dye. More details on the methodology, especially for experimenting the parameters and their effect on the formation of silver nanoparticles and perhaps the size of nanoparticles, we varied the temperature, reaction time, and examined the amount of extract when it's increased, and we examined the pH when it's adjusted and their influence on the formation of silver nanoparticles and size of the nanoparticles. Moving to the results for the phenol test and the GCMS. First, the Folin test analysis shows that the total phenol content in the coffee extract to be this amount, and phenols may involve in the synthesis of silver nanoparticles by interacting their carbonyl groups with silver ions. As studies reported, the reduction of silver ion in presence of phenols happens in two stages. First step or first stage is to start with the reduction of hydroxyl groups and followed by the oxidation of them to carbonyl groups, then a release of reactive hydrogen, which is responsible of the reduction of silver. In addition, the carbonyl groups also could prevent agglomeration after binding to the surface. Moving to the GCMS analysis, it was found that caffeine was among the three highest compounds in the extract. Based on the structure of caffeine, the reduction of silver may be assisted by caffeine molecules by contributing their electron from the carbonyl groups and the nitrogen atom in the rings. Furthermore, it was found that caffeine also can function as a capping agent in the synthesis, and the presence of rings improve the stabilization of silver nanoparticles and prevent inversion to silver ions again. Moving to the other part of the results, which is the effect of synthesis parameters, and first we start with temperature. Those results were obtained using UV-Vis. First, to start this experiment, we started with 45 Celsius incubation temperature for only 10 minutes of reaction time. We can see that when we used 45 Celsius and 60 Celsius incubation temperature, there was no formation of silver nanoparticles. Again, it was done only for 10 minutes, the reaction time. Then when the temperature is increased to 85 Celsius, during 10 minutes, we see formation of silver nanoparticles. So we can conclude that increasing the temperature increased the formation of silver nanoparticles. However, we cannot use such a high temperature when wanting to synthesize nanoparticles, because such a high temperature and high kinetic rate of reaction, kinetic energy, it can affect the stability of the nanoparticles and also can cause a loss of some bioactive compounds in the solution. Therefore, those particles cannot be taken for further applications such as catalysis. After the conclusion from the last experiment, we decided to start with reaction time of 15 minutes. 15 minutes and 60 Celsius incubation temperature. So we can see also that increasing the time caused the increase of the amount of silver nanoparticles formed during this time. And even from the solution, we can see it's getting darker, which means more silver nanoparticles in the solution. Another thing here, we assume those nanoparticles are the same size and shape because they are at the same wavelength. Here, the peak is at the same wavelength, which is almost 430 nanometer. The third parameter is amount of extract. Here we increase the amount of extract from 0.5 milli to 1 milli, also with 60 Celsius incubation temperature and 45 minutes. Here we can also see the solution is getting darker, meaning more silver nanoparticles are formed as well. And here we see the peak of formation is at the same wavelength as well, so we assume it's the same size and shape. And here the justification that more amount of extract cause more formation of silver nanoparticles, because in the extract itself, when it's increased, so that means there's more bioactive compounds in the solution which can interact with silver nitrate and reduce it. The fourth and yes, any problem? The fourth and most crucial parameter is pH. So here, the pH of coffee extract is 4. So we see there's formation of silver nanoparticles without any adjustment of pH. But when pH is 2, when we added an acid, we see no formation at all of silver nanoparticles according to the UV-Vis analysis. And with pH 10, we can see high formation of silver nanoparticles, and the peak of formation curve, and the peak curve is shifted to the left, which means it's a smaller wavelength, which means we assume it's a smaller size of nanoparticles formed here. So to confirm this assumption, we went for TEM analysis. This one, the first one, is at pH 4. We see there's a few nanoparticles of the size 50 nanometer and 45 nanometer. This one, it's at pH 2 with a small magnification. We cannot notice anything, and few nanoparticles are noticed when the magnification is bigger. At pH 10, the high pH, we see there's a lot of silver nanoparticles formed, and the size of them is ranging from 2 nanometer to 6 nanometer, which is relatively small, and we can conclude that we proved our assumption here that increasing pH will decrease the size of the synthesized silver nanoparticles and increase the rate of formation of them. Lastly, the catalytic activity. After we obtained the silver nanoparticles, they were tested as a catalyst to reduce methylene blue. First, we started with 0.5 milli of catalyst, and that caused the reaction to be very fast. Within 10 seconds, we got this flat curve, and the solution was turned to yellow. Therefore, some parameters in the experiment were adjusted, such as the amount of the catalyst. It was reduced to 50 microliter of the catalyst to be able to have this curve, so we can understand more the kinetic rate and the percentage of decolorization, and compare it to the results without a catalyst, so we can prove that silver nanoparticle can act as a catalyst. So here the blue one is without any catalyst, and the green one is compared with adding a catalyst for 1 hour. So we see that silver nanoparticles worked to speed the reaction and work as a catalyst. Here we notice another peak, and we assume this is because of the interaction and reaction between sodium borohydride, which is to reduce methylene blue, we added to reduce methylene blue, and between the catalyst, which caused more reduction of silver nanoparticles, as we can see it here at wavelength of 400, which is like same as before we saw the formation of silver nanoparticles at this wavelength. For the calculation, the reaction rate we see with catalyst is higher, and the decolorization percentage is higher with a catalyst. This reaction happened here is called the electron relay effect, where silver nanoparticles work as a donor of electrons for methylene blue, and here the electrons accepted by methylene blue will activate the methylene blue to be a redox catalyst and turn the color to a more colorless color. At the end, the results showed in this research showed that increasing temperature, time, and amount of extract resulted in an increasing amount of silver nanoparticles. Meanwhile, pH affected both size and amount of silver nanoparticles, and the synthesized silver nanoparticles also showed potential as catalysts in the reduction of methylene blue. However, this screen synthesis of silver nanoparticles should be studied further to achieve a controllable method and to allow a control of shape and size. And this method is in need to be optimized for going to scale up. On the other hand, and it's worth mentioning, the effect of light to activate the silver nanoparticles could also be investigated, as silver nanoparticles are also semiconductors which can function as a photocatalyst. At the end of my presentation, thank you everyone who attended this presentation, and special thanks to my supervisor, Dr. Rita. Thank you.
Okay, thank you, very much for Ms. Lama Alafandi for addressing this interesting topic. Right now, I deliver to the audience to ask a question to Ms. Lama Alafandi to for this interesting presentation. Any question from other presenter? If no question, I have a question, Ms. Lama Lavandi. I think this is very interesting, yeah, because I always drink a cup of coffee every day. Yeah, what is the main or important element or component from the coffee that extracted to be doped on the silver catalyst? And yeah.
Thank you for the question. So we only took like brewed coffee beans direct, and it was brewed, and there's no we just got the extract by diluting it, and we believe that the phenols in the coffee extract which is responsible of the reduction.
I think so many component in the coffee extract, isn't it?
Yes, the highest one is phenols.
Yeah. What is the role of the doped element on the catalysis mechanism of the silver catalyst?
Sorry, again?
The role of the component, yeah, from the coffee extract that doped on the silver catalyst in the catalysis mechanism, catalysis testing mechanism.
It's the electron relay effect, because silver nanoparticles will work to donate electrons. So it will activate the methylene blue as a redox catalyst.
Yeah, okay, thank you.
I answered your question.
Okay, any other question? If no more question for this presentation, I think this session for Ms. Lama is end, and let's give applause to Ms. Lama. Yeah.
Thank you.
Okay. Now we move to next speaker. I call Mr. Muhammad Luqman Hakim bin Hasim. Yeah. Time is yours to deliver your presentation. Time is yours. Yeah.
Okay, thank you, Prof. Just a minute while I share my screen.
Yeah.
And I hope you don't mind your moderator stealing your spot for a bit, I guess. Your moderator has to fulfill his PhD requirements. So I hope you don't mind. So without further ado, let me start. Everybody can see my screen clearly?
Yeah.
Okay, thank you, Prof. Okay, Assalamualaikum and good day to all of you. I'm Muhammad Luqman Hakim, your moderator, and now your presenter. I would like to present my work here, titled as in the screen. We are going to discuss the tandem hydrogenation esterification of furfural with a little bit of the kinetics using my catalyst. Without further ado, let us begin. So for introductions, I'll keep it very brief for my introductions, in the sense that let me just explain the demand of our energy these days. So as we all know, fossil fuel is in demand, is in high demand. However, the supply is actually in decline. Technology and ever increasing human population, that's what's contributing to the energy demand. But we now need, how do I put it, an alternative energy source to complement fossil fuel, not to replace it, but to complement it. And it would be better if that complementary energy fuel supply can actually be a green energy source. And therefore, we here are proposing that we apply biomass. So the good thing about biomass is it's actually a waste. So if we apply it and we use it, we are actually removing waste from our earth. So that works. So I'll focus on the yellow ones. So the biomass, we are going to process it through fast pyrolysis to yield bio oil. And that's our current product that we are planning to use. However, bio oil is not without any limitations. In fact, it has many limitations, despite its good potential. So one of its main drawbacks are the low energy value, untapped, but low energy value. It's corrosive, it's too viscous. So those are some of the, and it has short shelf life. Oh, that's a mouthful. Okay, so we need to upgrade it. There are many ways to upgrade it. However, today, for this work, I am focusing on hydrogenation and esterification, as my title implies. And we are going to do it, in fact, tandem. That means in one pot and as a continuous process. And we are going to upgrade it to biofuel. So speaking of bio oil, those problems I mentioned before, one of its main contributor, and the one that we are focusing on today, is actually the aldehyde furfural. So furfural is the main cause of aging for bio oil, hence why we are focusing on this particular bad guy. And it has relatively low energy value due to its structure, but we can do something about it. And furthermore, it shortens the shelf life of the bio oil by being very susceptible to polymerization, especially in the presence of acetic acid or any organic acid for that matter, which are abundant in bio oil. So if you see the problem now, we should also address furfural's possible reaction. And these are the ones that are available to us. But the ones that we are focusing on are furfuryl alcohol and furfuryl acetate, because those are the product of my targeted reaction, hydrogenation and esterification. And we are going to obtain them in tandem to each other. So furfuryl alcohol will be the starting material of furfuryl acetate. Why furfuryl alcohol? Because furfuryl alcohol has lots of fuel potential. The energy there, the energy is there for, to be used as a fuel source. While furfuryl acetate is actually a more stable form compared to any of all these compounds. So that's why we are aiming for it as well. Okay, now we look a bit at the past researches of now hydrogenation on furfural alone. What I want to draw your attention, my audience, to would be the products and the catalysts that they use. Mainly the products are, as you can see, varied, and it lacks so to say, a bit of, it could use a bit more selectivity, I could say. While the catalysts used are that yield good product, I must add, that yield good amount of product and selectivity are mainly palladium. There are also others such as gold that they apply. And as we can see, all of those are pretty expensive catalysts. And those are the things that we hope to rectify by the end of this. Now, specifically for hydrogenation esterification of furfural in tandem, that means one after another in one pot. The main problem I would say here, as you can see, are the low yield and selectivity towards furfuryl acetate. Why is that? It's because of the low amount of selectivity towards furfuryl alcohol itself, which will be the starting material of furfuryl acetate in this tandem reaction. And again, they apply palladium, which is relatively more expensive compared to the other transition metals that we are studying today. So here are the problem statements. The biomass, the fuel derived from biomass are actually low in energy and rapid aging, as I mentioned. And the catalysts are in need of more selectivity towards our targeted product. Specifically today, we are talking about furfuryl alcohol and furfuryl acetate. Now, we also need to, as you will see later, hopefully balance the surface acidity and basicity. And those are the main problems that we are going to tackle, hopefully, by the end of this presentation. Now, to go briefly of my aim and objective is to basically convert furfural to furfuryl alcohol and furfuryl acetate via tandem hydrogenation and esterification. How do we do that? We are going to use a trimetallic system, which I shall explain in methodology. And we are also going to study how the different variables such as temperature, pressure, and time actually affects them. So we are going to do that as soon as we get to experimental. Okay, let us go to experimental. Okay, I'll go through the basic structure of my research. So first and foremost, our support, the silica. So we are using rice husk ash derived silica. Why? Because we want to stick to the green concept that we are trying to apply here. Again, rice husk are actually a form of biomass waste, and we are converting it into catalysts that are going to produce green fuel. So I guess that's a cycle of its own. We are going to use those silica to support three metals that we have selected to study: copper, nickel, and palladium. These are the main ones that we select because of their innate capability to interact with furfural in the first place, and also of their ability to absorb hydrogen gas, which is important for the first part of our reaction, hydrogenation reaction. We are also introducing, as I said before, trimetallic system, aluminium into the system for the acid sites, which we will need, I'm sure you all know, for the esterification process. And we are also introducing magnesium oxide as a form of basic oxide to actually fine-tune our acidity of the overall catalyst. Now we are going to do all of this synthesis using our one-pot sol gel method, mainly due to create a strong bonds between each element of our catalyst via chemisorption, therefore hopefully preventing leaching process. Now on your left there, the catalyst batches are, as I stated, copper, nickel, palladium matched with aluminum and magnesium. On the right there are the materials I use. You may take a look at it. Okay, now we are moving on to the characterizations. These are the characterizations that I have used, for my characterization of my catalyst. I will explain them when the time comes. And I will also now briefly explain the catalyst synthesis process. Okay, basically, from the rice husk, we wash it with nitric acid, we calcine it, and then we got the rice husk ash, and then we extract the silica itself using sodium hydroxide, getting a basic solution. And then into the basic solution, we introduce our three metals, the transition metals, the active metals, the aluminium, and the basic oxide, magnesium oxide. And then we adjust the pH of the mixture into using nitric acid, added gradually into the desired pH, which in this case is pH 3. I forgot to mention that, sorry. And we are also after that, we washed, dried, and calcined to finally obtain our desired catalyst as stated there at the catalyst batches. So now, very briefly about our testing process. We are gonna use a batch reactor into the solvent of ethanol for the reaction. We will added the catalyst, the furfural, and also the acetic acid, so that we are gonna do as I said before, tandem hydrogenation esterification process in one pot. That means after hydrogenation take place, esterification will take place at the same catalyst. So just want to draw your attention to the varied reaction parameters, the temperature, the pressure, and the time there. Okay, we are finally entering the results and discussions. Okay, so for surface reducibility, we obtained this via TPDRO, temperature, and this is specifically temperature program reduction. The main point, I'm just gonna draw you to the main points of the results and the analysis. Copper has the highest reducibility compared to nickel and palladium, the copper system, I mean. Thank you. Its reduction temperature is at 400 compared to the others at 600. And we attributed this due to the much higher incorporation of aluminum and magnesium into the structure itself, leading to the distortion of electron cloud around the copper 2+ and easing the reduction. This will actually help in increasing the effectiveness of the hydrogenation portion of the reaction. So very briefly for pyridine FTIR, what we did was, okay, for pyridine FTIR, what we want to find out is which kind of acid are we dealing with, Bronsted or Lewis. So briefly, the peaks, if we compare the experimental and theoretical value here, so the DFT, as you can see on the left-hand side there, the DFT graph is actually the theoretical value. So the peak at 1536 and 1618 in the middle are the ones representing Bronsted. So I think you can all guess what I'm trying to get here is that comparing that to our experimental results, we are dealing with Bronsted acidity mainly here. And as our simulation actually is shown there, it's actually images of simulation. The pyridine ring is actually reacting strongly with the proton from the aluminium. And we confirm that Bronsted acidity is the one that exists on our catalyst, and that's good for our esterification process. Okay, structural and morphological. We did chemical analysis just now. We are focusing on structural now. And basically for XRD, the main point is that I want to draw you is that there is not that much difference in the catalyst system for it to be too different from one another, which makes sense since they are synthesized via the same process at the same parameters. However, as you can see, lattice strain and average crystallite size has increasing trend from copper to nickel and palladium. However, no actual collapse of the structure took place, as we shall see here. They are actually similar. The lattices are similar in the HRT images, which again, as I say, makes sense since they are similar in production. The BET also provides similar observations to us that surface area, pore volume, and pore diameter are very similar in terms of the value that they provide from one catalyst to another for there to be any significant difference to be made. So now let's jump to the actual conversion and selectivity data. So let me just draw you to the yellow bar there. Okay, mainly as you can see for actual conversion to sulfuric alcohol and sulfuric acetate, it requires a mild temperature. 150 degrees C is actually good for all catalysts. For 200 and 250, I believe they are more inclined towards cracking, hydrodeoxygenation processes, which will lead to furan, as you see just now in the past researches. So the same can be said for pressure as well. A mild pressure, relatively mild, I would say, 20 bar is what we need for sulfuric alcohol and good sulfuric acetate production. As for time, as you can see, generally, as you increase time, the product increases. However, that is not the case for some sulfuric acetate production in terms of nickel, because nickel is very, very prone towards production of hydrodeoxygenation product rather than hydrogenation product. Due to the structure of the, due to its inherent attractiveness towards fulfural's furan ring rather than its carbonyl carbon bond, which is what copper is actually very attracted to, as we discover here. So for the reaction kinetics itself, okay, you may be wondering what is Goldschmidt method. Basically, Goldschmidt method is just us applying the equation and below down there to calculate the constant for the production of esterification at the acid site. And what we discovered was copper was once again great, and it produces most at 150 degrees C, and it once again outperforms nickel and palladium even when we increase the time. So for another one, for TOF or sulfuric alcohol, we are looking at it as the end product, sulfuric alcohol and sulfuric acetate. So once again, copper is outperforming nickel and palladium. Nothing we can do about that for both sulfuric alcohol and sulfuric acetate. However, we can see the decline, the slight decline in after the increment for nickel in the production of sulfuric alcohol. And both nickel and palladium could not outright produce sulfuric acetate, just barely produce anything significant there. Okay, for the conclusion, basically in short, copper is good. It outright performs some other conventional noble metal based catalysts, such as PD, AL, SBA15. Thank you, Nurul. And this is very much due to copper's inherent ability to attach to its selectivity towards carbonyl carbon, which will lead to formation of sulfuric alcohol. And this is also helped by its good BET surface area and high dispersion. And that is all from me. I hope you enjoyed it. Thank you so much. I will leave the floor to Prof. Istadi. Thank you.
Thank you very much for Mr. Muhammad Lokman for your interesting presentation, I think, yeah. Okay, now I deliver the time to all audience to ask some question to Mr. Lokman to understand more in this topic. Okay, Any question?
Hi, this is Lee again.
Hi, Doctor.
Very nice presentations, Lokman. Just one more thing I want to ask about this copper-based catalyst. Do you perform any this leaching tests for your products? Because it looks like it's a very active and good selective catalyst, but what about the stability?
Okay, Doctor. I should inform all of our guests here that this is the middle part of my research for my PhD. So there's the beginning part, and then this is right in the middle, and there's one at the end there, PH study. So we did perform it. We did in fact perform recyclability tests, and we did perform repeatability tests. And I can inform you that the results are looking good for copper. There are still reduction in terms of decrement in terms of the performance, but it's not outright. It's way better than the baseline that we set, which is just rice husk silica and just copper. So the aluminum and magnesium is actually helping to improve the stability due to the strong chemisorption and the interaction that they created within the matrix of the overall catalyst. But I did not include it here to answer your question, but I did do it.
Yeah,
I hope
sure.
that helps.
Yeah, thanks. Because I just need some confirmations from you about the leaching text. Yes. Okay, thank you.
Thank you, Doctor.
Okay, any other question? I have a question, Mr. Lokman.
Okay, go ahead, Prof.
Okay, I wonder your catalyst is contains so many metals.
Okay.
So, which one the metal that most significant role on the hybrid hydrogenation and esterification?
Okay, Prof. If you want me to give a favoritism answer, I would say it's the copper, because without the copper, the reaction will not be able to start. But with that said, I would like to give some love to aluminium and magnesium, because as I think I should mention that the role of magnesium is not that prominent in this presentation, because we are not focused on the acid site itself. We are looking at the overall kinetics and the reaction that took place. However, magnesium actually plays a vital role in actually developing a stable catalyst to be able to actually carry out the esterification process. As I said, strong acid sites will actually not be able to esterify. They will actually crack the furfural to form furan or something else. But if you want my answer about which one is my favorite, it's actually copper. I appreciate copper the most for high selectivity towards furfural alcohol.
Regarding to the acid side, which one is more dominant between the bronze state or Lewis acid side?
As my pyridine FTIR result suggested, we strongly believe, and we are quite sure that it's definitely the Bronsted acid site, because the peak is way more prominent. The two peaks in the middle are way more prominent and they represent Bronsted acid site. There is one shoulder peak at 1,400, if I'm not mistaken, that represents Lewis acid, but they are not that prominent compared to Bronsted. So to answer your question, Bronsted acid sites.
Yeah, I think Bronsted acid site is quite okay for the support to the esterification, isn't it?
Yes, bro.
Okay. Any other more question? If no, I think session of the Mr. Muhammad Lokman is ends, and thank you very much to Mr. Lokman for your great presentation. And let us give applause to Mr. Lokman. Thank you. Now,
can we interrupt for a photo session for a
while? Okay.
Yes, Doctor. Sorry, as my colleague pointed out, we need to take a photo for all of us. So I would appreciate if all of us could just turn on our camera. All right, Dr. Said, if you would join us.
Yes.
Hi, Doctor. Nice to see you.
Hello.
Okay, I will take our picture in 1, 2, 3. Okay, I got it. Okay, hold on. One more picture for full screen. Thank you.
Thank
1,
you.
2,
Thank
3.
you.
Okay, it's done. Thank you.
Okay, thank you. Uh, right now, we will continue to the next session is the presentation for the invited speaker from Dr. Wee Woon Lee. You have 25 minutes, isn't it? 25 minutes to present your works, and we continue with 10 minutes for the ask and question. Okay, for Dr. Wee Woon Lee, time is yours.
Okay, thank you, Prof. Study.
Thank you.
I would like to request for the pre-recorded videos from the IT personnel. Can you help me to share the videos? Because I worry that my
Okay, I'll
connection
share right away.
is unstable.
Thank you,
Yeah,
Doctor.
thank you.
Hi, very good days to everyone.
Oops. Share audio.
Hi, very
Oh, sorry. 1 minute. Full screen.
good days to everyone. So I'm Lee from Nanotechnology University, Malaysia. And in this session, I would like to share the topics of efficiency, the oxygenations of biomass to hydrocarbons based biochemicals over the mesoporous catalyst. So the contents of my presentation slide will be mainly focused on the conversions of biomass into the liquid hydrocarbon fractions. And besides, the topics covers the mesoporous catalyst that is used for the deoxygenation process, and how is the synergistic effect between the active metals and also with the catalyst support, so that is affect the catalytic activities of this deoxygenation process. Malaysia is a tropical country that has a large amount of the biomass residues, so such as the oil palm biomass, which is generated from the plantations and milling activity, and it is the largest amount of the biomass, which followed by the municipal solid waste, and then the wood industry, followed by these agricultural waste such as the rice husk, rice straw, and also the sugarcane bagasse. Okay, so the oil palm industry producing the largest amount of the biomass in Malaysia, and it is approximately of the 85% out of the 70 million tons of the biomass generated. So Malaysia is able to generate sufficient amount of the dry palm biomass, and these solid residues that left from the palm oil industries includes the oil palm fronds, which is the leaves that is dropped or cut off from the trees, and also we have this oil palm trunk, which is the tree that is discarded for replantations after year end of this life cycle. And we have these oil palm species such as the anti-fruit bunches, we have the palm kernel shells, and also the mesocarp fibrils that is generated during the milling process, such as the activities of the palm oil extractions and also the oil refining process. So this is an infographic about the gross nation's income contributed from the biomass application. And this data is prepared by the National Biomass Strategies 2020 report. And based on the data here, biomass-derived product greatly impact the nation's incomes, where the bio-based chemical as well as the biofuels potentially offer the highest values, and followed by the palm-based pellets markets, which is used for the heating purpose. And then we have these wood products, basically is used for the constructions and furniture applications, as well as we have miners bioenergy applications, where the biomass may be turned into the syngas, bioethanol, or biogas for further fuels or transportation purpose. So how does the chemistry behind the biomass that can convert the palm waste residues into the wealth? And this is the inner image of plant cell walls of the biomass. The cellulose fibrils, which is in green colors, it will group together into a fiber form and in the hexagonal structures, and surrounded by various types of polymers like hemicellulose, which is in the light green colors, as well as the bulky lignin, which is in the green colors. As refers to the chemical formulas for these three major components that is acid in the biomass, okay, so we can see there's a lot of this carbon content in all these components, right? So this is considered a variable form of the carbon source that can be fully utilized before it would be released back into the atmosphere in the form of carbon dioxide. And we can see the difference from the oil palm biomass, such as the EFP and different bunches OPF from the palm fronts, palm trunks, palm kernel shanks, and also the palm fibers. So they have a different contents of the cellulose, hemicellulose, and lignins. And in order to fully utilize the beauties of this biomass for various applications, it is necessary to unlock the chemistry code of these nature's resources for further efficient process in forms of biochemicals as well as the biofuel. Now let me define the biomass feedstock that is used in these projects for the hydrocarbons, such as the biochemicals and also the biofuel productions. So the feedstock here is the biomass-derived bio-oil, and this is the bio-oil that is produced from all different kinds of the solid biomass materials, such as from the palm biomass, agricultural crops materials. Okay, it will undergo the pyrolysis process in the absence of oxygen in order to produce the black colors of liquid, which we know as the bio-oil. However, the bio-oil cannot directly for further applications due to some limitations, such as it has this high oxygen content, which is unstable during the storage purpose, and it is with high acidities, high viscosities, very low heating values that cannot use for the fuels or heating process, and it shows a high polar component, which is incompatible with the organics or petrol-based fuels mixings. And then it is also chemically unstable, right? So the major components of the bio-oil is waters and the lignin fragments, right? So this lignin fragments is actually all these phenolic compounds. Okay, it is present in the ring type of structure, which is potentially to be fit into those petrol-based structures for chemicals and fuels applications. That's why here we come with the operating process, which to remove all these oxygen atoms in order to achieve the higher contents of the hydrogens to carbon ratios, which can help to improve the qualities of the final products for the biochemicals and also for the biofuel productions. The biomass upgrading process that involves the removal of the oxygenates can be conducted by using the deoxygenation process in the presence of catalyst. And the process can be occur with various of reactions pathway based on the reactions conditions and also the gas carriers. So for example, the decarboxylations and decarbonylation pathway occur in the inert conditions where the oxygen compounds will be removed in the form of CO2 and also the carbon monoxide, okay, through these two reactions pathway. So in the presence of hydrogen gas flow, hydrodeoxygenation, which usually we call it HDO process, will be occur in order to remove the oxygens in the form of water molecules. And other side reactions such as hydrolysis and cracking process do help in the deoxygenation process and is usually occur in high reaction temperature. In order to enhance the efficiencies of the DO process with high yields and high selectivities of products, so one of the important criteria that our group focus is deoxygenation catalyst. And it has been reported that the key characteristics of the deoxygenation catalyst should be consistent of the high or large surface areas of porosity, which help to enhance the accessibility of feedstock with the catalyst during the reactions. Okay, so secondly is about the high acidities of the catalyst, which can favor for the desired reactions pathways that I mentioned in the previous slide. And also the thirdly is the presence of the redox site that promote the hydrogenation functionalities of the feedstock. And thus the mesoporous silica was selected for the deoxygenation process, which is due to its advanced properties such as chemical, thermal, and mechanical stability. And it shows the high surface areas. It has suitable dimensions or pore size, which is mesopores that is able to fit in the lignin-based compounds, and it has this high dispersions for the active metal size. So other than the mesopores supports the active components such as the transition metals as well as the rare earth metals are very suitable to improve the overall of the catalyst because it can help to improve these acidities as well as the redox size to provide the synergistic effect between the catalyst support as well as the active side of the metal. Thus, the present studies aims are to develop the mesoporous-based catalyst for the oxygenation process. The second is to produce the biomass-derived biochemicals or biofuel via the deoxygenation process. So this project is aligned with the Sustainable Development Goals, which the goals number 7, affordable and clean energies, and goal number 9, which is aligned with this industry innovations and infrastructure strategies, as well as the goal number 13, which is about the climate change. Here come with our research findings. This study utilized the lignin-derived bio-oil model compound, which is GoEco, for the production of cyclohexane, which is one of the compounds that is high demand in the chemicals and fuel market. So the hydrodeoxygenation reactions is the main reactions pathway in the presence of hydrogen gas. And the catalyst developed here is bimetallic nickel copper, supported by the modified mesoporous silica, which the titanium is docked on the MCM41 support. The advance of this catalyst is that the titanium dopants can help to improve the acidity, which is both the Lewis and Bronsted size of the catalyst support, and provide the redox active site for the reaction as well. This is the scope of studies where our focus are preparing the copper nickel bimetallic where it is supported by using this titanium dot MCM41 catalyst. And also we'll focus on the investigations on the catalytic activities of the hydrodeoxygenation process by using the bio-oil lignin compound, which is white coal. So as the mesoporous silica MCM41 is mild acidic in nature, that's why here's come with the modifications in order to improve the properties of this catalyst support by incorporate this titanium metal salts through the hydrothermal process, and it's helped to improve the both Lewis and the bronzes acid size of the catalyst, as well as it also can be improved the redox size of the catalyst. So the prepared catalyst will be first reduced in the hydrogen gas at around 550 Celsius for 5 hours, and then the reduced catalyst will be kept in the glass bag, and it will sealed before the commencement of the reactions. And for the hydrodeoxygenation process is conducted in the pressure reactors where under these experimental conditions, okay, in the presence of the hydrogen gas. And the final product will be analyzed by using the GCFID as well as the GCMS for the quantities and quality studies. The physical chemical properties of the modified MCM41 support as well as the final catalyst will be discussed here. These are the microstructures properties of the MCM41 support that with and without the titanium dopant. Okay, so based on the chemical characteristics, which is the SRD characterization, which indicate that the formations of the hexagonal mesopore structures for the MCM41s, okay, while we can see there is a slight distortions of the hexagonal structures for this modified MCM41, which is due to the larger bonds length of the titanium oxygen silica as compared to the silica oxygen and silica linkage here. So now we look at this FDIR result. So based on this FDIR result, we can indicate that there is a presence of this linkage, which is titanium oxygen with linkage that's present in this modified support, while the pure MCM41 shows the presence of the linkage between the hydroxyl group with the silicates, as well as the linkage between the silica oxygens and silicas. Okay, so for this UV vis analysis, it shows an intense peak for this modified silica support, which is indicate that the presence of these tetrahedral coordinations environments for these titanium cations that is incorporated into this oxygen and ion. While for this pure MCM41, it is indicate the absence of the metals to the ligand charge transpose within these hexagonal mesostructures, because it is absence of this intense peak here. So next, we look at the textural profiles of the modified support, and both support shows type 4 of the absorption isotopes from this BT analysis. This indicate that the mesoporous natures of the materials, and we can find that there's a slight difference between the pore diameters, which is pore size, where the modified MCM41 shows a largest of pore size as compared to the pure MCM41. Okay, so this is due to the incorporations of the titaniums into the hexagonal structures of the mesoporous silica MCM41, and that's why it leads to the whiteness of the mesopore for the TI dot MCM41s, because there's the largest ionic radius for the titanium species as compared to the silica species here. Okay, so for the surface areas, it is found that the MCM41 shows the battles and higher surface areas as compared to the modified MCM41. Also because this is due to the collapse of the mesoporous structures of the NCM silicate structures once there's incorporations with a denser titanium species. Okay, so for the acidity study, we're using the TBT with ammonia gas, okay, studies, and this indicate that the modified MCM shows the higher concentrations of the acid size as compared to the pure MCM41 support. And this reveals the favorable role of these titanium species where it really helps in improve the acidic properties of the overall of the silica support. The internal microscopic structures of this modified MCM41 was analyzed by using the Tem Analysis. So the image is clearly shows the parallel arrangements of these mesoporous channels for the modified support, and it is present in the form of these honeycomb-like structures, right? So based on the figures here, there have no visible titanium particle dispersions in this TM image, which indicate that there is a well dispersion of this titanium species that is within the framework of the mesoporous silicate structure. The oxidations and chemical stage of the surface elements, and also the type of the chemical linkage that is available for this modified titanium MCM41 support was determined by using the SPS analysis. So based on the analysis, this indicates the presence of the linkage between the silica oxygens and titaniums, which it is reveals that there are the substitutions of the silicate ion with the titanium ion, especially in the hexagonal mesoporous silica structures. Now we will discuss on the final catalyst, which is the bimetallic copper nickel oxide that is supported with the MCM41s or modified MCM41s based on the chemical structures and the reducibility properties. So based on the SRD analysis, it is found that the copper oxide species for both samples could not be observed, which is due to the small particle size of the copper species, and this resulted better dispersions within the mesoporous support, either the modified and unmodified mesoporous support. Okay, so for the TPR analysis, the reducibility patterns of catalysts, especially for this modified silica support, is slightly different from the pure MCM41 catalyst. Okay, it shows that there are three reduction peaks that is present in the finals of the analysis, and the reductions peak indicated that there's a presence of the strong interactions between the copper oxides and also the nickel oxides, which is lead to the shifting of both peaks, which is the copper oxides and also this mixed copper nickel oxide, and they are shift to a lower temperature, okay, which is as compared to the catalyst without modifications, which is the reduction temperature is higher. So besides, there is an extra peaks that is present for nickel oxide reductions, which it is due to the presence of the interactions between the nickel with the titanium MCM41 support. So it leads to another new active site for the reductions process. So based on the SPS analysis, the existence of this nickel and also the coppers in the bimetallic stage is confirms the formations of these nickel copper alloys in the supported catalyst, and this can help to enhance the synergistic effects towards the deoxygenation process. Now we will discuss about the catalytic activities about the prepared catalyst by investigate the hydrodeoxygenations of glycol, and the desired product from the HDO process is cyclohexanes. Okay, and for the HDO activities, the result that we are concerned is the glycol conversions and also the product selectivities, and this is compared with both catalysts, which is fresh MCM41 and also the modified MCM41 catalyst. Okay, so based on the result, it is indicate that the titanium doped MCM41 catalyst renders the highest glycol conversions as well as the cyclohexanes selectivities. And when we look at these product distributions here, it is indicate that the modified catalyst renders much more selective of reactions pathway as compared to the pure MCM41 based catalyzed process. And here we can be summarize that the presence of the acid sites, which is from this modified MCM41, is play a major role in the oxygen's removal through this dehydrations or the desired hydrolysis process, as well as all these decarbonylations and decarboxylations process, whereas the hydrogenations of glycol is promoted to the cyclohexane products through this redox site, which is contribute from this active metal sites as well as the titanium dopes. Yes. The effect of reactions pressures on the glycol conversions and the cyclohexane selectivities was further investigated by using this copper nickel supported titanium MCM41 catalyst. So based on the result, it is indicate that the higher hydrogen pressures can be positively improve the glycol conversions and as well as enhance the product selectivities of these phenolic compounds into the cyclohexanes, which is the cyclic hydrocarbons compound. So based on the analysis that we have done, so the group has successfully to summarize the real deoxygenation pathway for the conversions of glycol into the cyclohexanes by using our developed catalyst here. And first, the glycol will undergo the demethylation process in order to remove this methyl group through the acid sites of the catalyst, and it will form the phenol, which further undergoes the hydrogenation process, okay, in the presence of the metal sites of the catalyst in order to form the cyclohexanone in the ketone form. And then hydrogenations will be further to be processed with the presence of acid sites in this case, okay, in order to reduce the double bonds into a single bond in the form of the alcohol cyclohexanol, and further dehydration process to remove the hydroxyl group in the presence of the metal sites, okay, in order to form these cyclohexanes, okay, and continue with this hydrogenation process in the presence of metal sites, and we will got our cyclohexane product. As a summary here, the developed titanium MCM41 mesosphere support was successfully to be synthesized by using these hydrothermal methods, and this developed catalyst shows the largest surface areas, medium size of mesopores, hexagonal pore geometry, strong acidic sites, and well-dispersed redox sites, which is a potential catalyst for this deoxygenation process. And for the catalytic activity study, it indicates that this developed catalyst shows a higher glycol conversions, which is around 90%, with a high product selectivities to 50% as compared to the unmodified catalyst. And if you wish to know more about the projects or related studies, you may access to these articles here. This is the end of my presentations. So you may contact me if you have more inquiries or you are interested about the project. Thank you very much.
Thank you very much for Dr. Hui Won Lee for delivering the quite interesting presentation. And now I open the ask and question to all audience. You can deliver directly live or via the chat. Any question for all the audience?
I guess everyone is tired already.
Okay, I will ask to you, Dr. Hui Won Lee. I think this is very interesting research. Yeah. My question is how to adjust the catalyst in terms of acid sites, maybe bronze state or Lewis, to more support the deoxygenation reaction mechanism of hydroxycarbon of biomass, because currently I also works on the cracking of palm oil to gasoline, kerosene, and biodiesel. I think this is similar.
Yeah, thank you, Prof. Study. Basically, for my perspective, both the metals, the active metals that I suggest, like the transition metals as well as the rare earth metals, they playing a role other than the kinds of redox sites. They are playing the role in the acid sites, tunable acid sites, right? So one more criteria is, I think, the catalyst support. For example, like those carbon-based supports and also the silica-based alumina, they have a slight acidities, right? They can further improve with those kind of metals and support interactions, or some of the functionalizations, right, with the catalyst support in order to improve the acidity. So what about the bronzed and also the Lewis site? We know that the bronzed site, they are in theoreticals, they might have the OH, right? OH site. To promote the bronzed site, while the Lewis site usually is from the metal oxide phase in order to create the Lewis acidity. Yeah, this is very theoreticals and fundamentals chemistry that we try to use in order to apply and to kill the basic and bronzed site. But although but in reality, in experimental value, it is very hard for us to determine, we want this concentrations, or we want this percentage of the bronzed or the Lewis, right? Unless we have many experimental data, and also we have tried many these parameter study in order to study the concentrations of the metals or modifications for the catalyst support. So this is my understanding.
We call it as only acid sites, isn't it? To cover the bronze state and also the Lewis side. The second question is, which one the catalyst properties that most dominant effect on the reaction between the surface area and then the acid side and the redox side, surface area, acid side, and redox side. Which one is the more dominant, or maybe three parameters should be combined all together?
Because for my presentations, I highlight things that the three important factors, right? Surface area, but I personally think that the active site is very is the major factors that to influence the catalytic activities and also the product selectivity. Just the catalytic activity and conversions. While the surface or the porosities of the catalyst, it can use to control those product selectivity, because it's only allowed a certain type of feedstock or the what to say reactions immediates to be react during the porosities. Yeah, so in fact, the tree is quite important. But to initiate the reactions, I think the active site is very important. Let's talk about the redox and acidities or basicities. Yeah.
Yeah, I think the acidity is quite significant effect on the deoxygenation, I think.
Yeah, yes, you're right, Prof. Yeah.
Yeah.
Yes.
Okay, thank you.
One more thing is they need the suitable conditions. Temperatures and pressure is another very important factor to boost the reactions.
Yeah.
Right.
I think very interesting idea.
Yeah.
Okay.
Okay, thank you.
Okay, any other question from the other presenter? Yeah, we have 3 other presenters here.
Yeah, I think Lukman's and the rest of the presenters all working on the catalyst quite similar. Our studies are quite similar.
Yeah.
But they are tired already, I think. Yeah. I think we can have more connections during some networkings after this.
Yeah, I also works on the cracking of the palm oil to fuel.
I see.
Yeah. I think because Indonesia and Malaysia have palm oil, abundant of palm oil.
Oh, it's good. Yeah. This is a quite interesting study, especially now. I think we are really move into biomass
Biomass or vegetable oil. In our country is palm oil. I think is more the most commodities that we have to change to renewable energy.
This is
okay. I think very interesting. If no other question, I think our session is ends, and thank you for the last presentation from Dr. Won Lee, and we let us applause to all of the presenter here. Thank you, and ladies and gentlemen, thank you for your attention and contribution in this conference. Thank you for the cooperation. Assalamualaikum warahmatullahi wabarakatuh.
Prof.
Yeah.
Prof.
Yes.
We need to announce the best presenter, but we are.
Okay. I forget that.
Few more minutes.
Yeah. Okay.
Okay. Let's hold on.
Okay, we will have the best presenter in this session, and we will announce a minute. Yeah. We wait. We have to wait a minute from the moderator to prepare the certificate. Okay. Now we will reach the end of the session. Yeah. Now I will announce the best session presenter here. Now I am very honored to announce the best presenter for this session. Is goes to Mr. Muhammad Lokman Hakim. Yeah, congratulations to Mr. Muhammad Lokman Hakim, and congratulations. Let us give applause to Mr. Lokman. Okay.
Thank you, Prof. Thank you, everyone.
Yeah, and now we reach the end of this session. Thank you for the participation of all presenter, and then the committee, and then the IT committee. Yeah, see you again in next conference, I think. Assalamualaikum warahmatullahi wabarakatuh. I forward to the committee for this session. Thank you.
You are mute. You are mute. Lukman, you are mute.
Master Lokman still muted.
Okay, I guess that's all from us today. Okay, so thank you everyone. Well done.